Hello, everybody. I'm Justin Cormack, and I'm going to talk to you about kind of operating system things you can do with Linux and trying to be practical while also trying to make things better. I'm based in Cambridge. I was reminded by the Code Mesh logo. This is just up the road from where I live in Cambridge. It's kind of iconic Cambridge thing as far as I'm concerned. Cambridge is a village that does tech, and the farmland grows telescopes rather than crops, and it kind of feels like that. So I moved from London, and it still feels kind of it's an interesting place. I work at Docker in Cambridge, mainly on open source projects at Docker. And I'm going to tell you a little bit about kind of how I got here and why I think this is interesting and why I think you might find this interesting. Way back in the 90s, which I was reminded of having met Sophia yesterday, I was at Imperial, and I learned simultaneously. I learned both Haskell and Linux sysadmin as a sort of simultaneous thing, which was a kind of weird combination, I suppose, but that's the way. And Miranda as well, for that matter. But then Haskell. And for a long time, I've been both a developer and someone who gets involved in operations and actually running stuff. And they're very different communities, and I kind of, why can't we have nice things in operations too? Why, we have nice programming languages, but when you actually operate computers, it's kind of horrible still. Over the years, I've worked in industry a lot, and I've been quite pragmatic about actually shipping things, because shipping things is fun, and people use things, and you get feedback, and it's great. And having people use something you've built for doing something really exciting is great fun. But I'm also an idealist at heart. I think we really can do better with what we ship. And so this talk is kind of also about trying to do a combination of the pragmatic and the practical, and also trying to keep the dream of making things better alive as you do that. I'm going to talk about a project I've been working on for a few years now, actually, but it's been open source for 6 months. Back in 2015, when I started, when I first started at Docker, they gave us a little project to work on, which was Docker for Mac, which was as a sort of integrate into the company project. And one of the components we needed in that was we had to run Linux in order to build containers. And I've worked on and off in embedded Linux systems for quite a long time, and they're all horrible to work with, and I really didn't like them at all. And if you look back in the history of LinuxKit repo, the first commit is just a list of kind of useful guidelines for what we want to build. And one of the things it said was not required, self-update. Treat this thing as immutable. We want to build an appliance. And that's been the kind of philosophy, and it kind of came out of some ideas around immutable delivery that has kind of interested me for a long time. From 2013, and this is something that, as a sysadmin, I always sort of resonated with me. If you get a system that's been running for a long time, you really have no idea what state it's in, what's happened with it. Things have changed, and you don't know what they are. If you know it's never changed, you know what state your system is. Back in 2011, Netflix started doing immutable delivery of servers. They said, we don't ever change anything in production. We just make a new one, so always know the state. But this kind of process has not become the normal way that people run servers still, and it's still kind of disappointing. But it's always something that struck me as logical, and from my experience of maintaining state over time, this was always something that really was important to me. Another thing that's always been important for me, I've kind of worked in industry, is design for mass production. When you build things that are going to be mass produced and operating, computers and systems are now mass produced items, you design them for mass production. The Ethernet cable is designed to be made for almost no money at all. It's designed to be customized. You can make cables different lengths. You can terminate them by hand and things like that. But mostly they're just mass produced now. You don't even the days of terminating your Ethernet connections by hand are kind of less common now. But it can be done. And there's the thing is built with tooling. There's a crimping tool. Every cable in a data center has its own crimping tool. And a set of tools for customizing it. But it's you don't build things that then you craft and make them expensive. You have to make things really cheap if they're going to be mass produced. And that's kind of always was in the back of my mind around this as well. And state, state, things get in a real mess if you don't control state. I think some of the lessons from functional programming were that uncontrolled state updates are a total nightmare and will make your systems unmaintainable. And there is state, but it's controlled state. You know where the state changes. You know where the state lives. You know how the control of state happens. And can we apply some of this thinking a little bit to operating systems? I want to go a little diversion kind of on the way there, though. I worked on unikernels and still do for many years. And unikernels were this great idea about why do we even need an operating system? Why are we building systems based on Linux and other operating systems? This is, do we need to do this at all? A unikernel basically says, an operating system gives me a bunch of services and code that I want to use. Why isn't that a library? Because that's how I consume all the other code I use. And this kind of simple idea of a library operating system or libraries for code is really quite powerful, really cool, and it's becoming relatively practical. There are real systems, Mirage OS, Alvim, Include OS, and Erlang on Zen are kind of the biggest examples. These are used in production in niche areas generally. They're used in niche areas partly because all the system code is not written as libraries by default. The Linux TCP/IP stack is very difficult to use as a library. I mean, there are people who are trying to make it work like that, but it's really, really hard. It's not built like that. It's not maintained like that. It's not designed to be linked into your program. So mostly everything's been written from scratch. So it's slow work building production-grade libraries for everything an operating system does. The predominant use cases so far have been various kinds of network appliances and often kind of stateless things. But the production use cases are real, and if you can use these things, I recommend giving them a go, trying them out. There's a particular overlap between functional programming languages and unikernels, which is great. But they tend to run as virtual machines, and they tend to still have an operating system underneath that. You still have to deploy them. There are loads of problems in production, like cloud providers don't provide the right size VMs for the kinds of things you want to do with the unikernels. You want loads and loads of small ones, usually. So they're still kind of new and still trying to persuade people that that's the way to deploy in production. And so in reality, the vast majority of people are deploying on Linux, mostly, sometimes on Windows and other operating systems. But let's say in a pragmatic world, what do we need to run on Linux in a nicer kind of way? I work for Docker. We do containers. Containers are a great way of packaging applications. And one of the things you notice when you use containers is that you don't really need much inside your containers. Generally, the nice thing about them is you can just package your application. You don't need much operating system. You can get rid of it all. You can have a static linked executable inside, or a few libraries, maybe some certificates and some secrets at runtime, that kind of thing. And it really kind of focuses people's minds on, I want to run my application, not how do I want to run my application on this operating system. So that was kind of already kind of stage one of, we've got people that we see people that have learned kind of to package up their application in a standalone way that doesn't involve building a whole Linux server, which is a good start. And then all we need underneath that really is enough Linux to actually run these containers that people have packaged up. So the kind of iteration process with LinuxKit was finding out what you really need to actually do a completely minimalist boot. You need an init system. You need to configure all the things that Linux doesn't configure for you, like devices. You might need to format a disk and mount it. Have some program to run containers. We use containerd, which is a kind of minimalist container runtime that's much smaller than Docker itself. It's a component of Docker now. And then you run system things like DHCP and containers. It's you could just use systemd. Systemd, I think, is still too complicated for the minimalist thing. This is really a few hundred lines of code, and it's kind of relatively straightforward and manageable. So the kind of thing we designed with LinuxKit is a kind of kit. It's designed to get you started. It's not opinionated. It's totally designed to be built in a CI pipeline. It's not, it's not complicated. I'll show you in it. Build times are a couple of minutes at most. Test locally, ship to production. Small, minimal, fast boot. And it's got a very simple structure. Some sequential startup to configure things, and then you run a number of services, which are your application, which might be a few containers. It's really kind of simple. It's actually the same design as kind of pods and Kubernetes. It's kind of it's a kind of natural, simple design. Sequential start because it's predictable, and then run everything once everything's configured. We have a Yambol file for config, which I'll show you in a demo. Yes, I'm just going to show you because we've got just an example YAML file here. We have the basic stuff, certificates, DHCP. We have long version numbers, which are hashes of Git tree hashes. And this one just runs Nginx, standard Nginx image, and it has a few other config about trust. We can just build this. This is total kind of defaults to run locally, but there's some more complicated options. You see, it's assembling our operating system, nice and quick. It's a bit slow actually. When you make when you reduce something down from taking a few hours to build to a minute, then you get annoyed that it doesn't take 2 seconds. So it's kind of annoyingly slow now because it's not long enough to go and make a cup of coffee anymore. And then we can run this image we've produced. In theory. That's never not run. Oops. Okay. And we've booted up the system, and it's running a very minimal system, so it hasn't even got curl. There's a console to log in, which is obviously entirely optional, and you can see we've got the welcome to Nginx. So we created an operating system. It's there. It's got an address from DHCP, and it's only got exactly what we configured. It's very straightforward. There's really not very much in there at all. And when we've finished with it, we can shut it down. It has the shutdown message. It's also in the config file. That's kind of how I feel that's kind of how you should. Let's go full screen again. That's kind of how you should kind of consume Linux. I think it's not a different. We're not making someone change to not using Linux, but it's a new way of consuming it that's much, much simpler. The root file system is immutable. You can run it from an ISO or anything. There's no package manager because we're never going to do any updates. It's going to just correspond exactly to how you specified it. If you want to update it, throw it away, build a new one. If you really want dynamic services, you can run Docker or something that runs, or you can actually run containers dynamically if you really want, but there's no particular need to. And you really cut down on all the sort of complexity of installation and things like that. You just have a script, build it, run it, does what you want, kind of appliance model. Particularly for this audience, people always say, "Oh, Nixos, isn't that the same, different? What is it? Why didn't you use Nixos?" It's a question that comes up quite a lot. They're definitely very different kind of things. Nixos has still got a package manager. It's designed as a better package manager, but it's still designed to be updated in a very controlled way, but it's designed to be updated. We don't even have a package manager. There's absolutely no reason why you shouldn't use Next to build the containers for LinuxKit. It's great for building containers. And the other way around, there's now, as of this morning, I came across this, there's now a LinuxKit-based container builder for Nix, so you can use, for the Mac. You can use both absolutely together, and they're complementary, I think. I kind of summarize it as Nixos is for sort of more obedient pets that, they're totally controlled, whereas LinuxKit is really designed for mass production of computers, where you really don't want to do this kind of update and maintain thing. But they're definitely complementary and different kind of approaches to things. I think LinuxKit is designed also to be really approachable and easy for people who, and we found people can try it out and work out how to use it in a few minutes, which I think is really great. You don't have to invest a huge amount in it. We kind of do this through a lot of sort of practicalities. There's loads of tooling built in, so you can build any kind of image you want, ISOs, you can build cloud images directly, you can build VHDs and raw disks and Raspberry Pi images, and so we have a whole set of tooling around common use cases for going into production, QCOW images and all sorts of stuff, and these are really quite easy to add. And then there's a simple developer-style workflow, build, push, run, so you can build these images, push them to AWS as an AMI, run it in Amazon using tools. We have the desktop kind of things I showed you, because that's so you can run it locally on Mac or Windows or Linux without any issues. You can totally use Linux, without having a Linux machine, which I think is really nice, because I think that Linux is great for appliances, but you don't necessarily want to use it as your day-to-day system. A lot of people don't. You can use it on all sorts of things like vCenter and OpenStack and all sorts of whatever people use. People come along and produce these things, which is really nice. As I said, there's a really simple build, push, run kind of set up, designed for normal use. So if you run it on Google Cloud, it behaves exactly the same as the example I showed you, except it'll be running remotely. You'll get the console and the login and everything exactly the same. State. I talked about state earlier. State is obviously really important. The example I showed you didn't have any state, which is great for some things, but lots of real applications have state. So we kind of divide things up. So the file system and the image you build is totally immutable. It's like your program or your function. You can pass in some config for secrets and things, and then you can add disks for persistence, and you know that all persistent state will be on those disks because nothing else can be modified. And then you can manage these disks as your data sets. You can reattach them to other machines if they're network-attached disks, or for physical disks and things like that, we're looking at tooling for doing nice snapshot, restore, move disks to somewhere else, and kind of maintain your state as a thing that you can have control of. So code, config, and mutable state, all cleanly separated and managed separately. Most of the time, the way people use it, they just have a single volume for state, and so it's really sort of, you can imagine it. So everything that you want to persist goes on this external chunk of data, the volume. Ideally, it's just the data from your one application, because the system itself doesn't need any state. So your application writes its database to that volume, and you know that if you snapshot that volume, that's your application state, and then you can unsnapshot it somewhere else, back it up, restore it, or whatever. And all there is on that is your application state. It's not the system state, because the system is designed to be totally stateless and just dynamically configure things, other than any kind of config like secrets, access keys, and things like that, which you obviously need to pass in separately. And you kind of get to sort of systems as functions I mean, I definitely like to look at them like that, because it fits my kind of mental model that a stateless machine is a simple function with no arguments, and everything else you should be designing with this kind of model of I have one application, it has a chunk of storage that's its input state. If you re-execute that machine from the same state, it should behave in the same way. If you take that state and put it somewhere else and boot the same function, i.e. the same machine image, it should behave the same way. And you can you have this kind of model of mental model of your operating system as in this nice, clean, well-structured kind of way. And I think that's definitely a much simpler, nicer way of modeling stuff. It's definitely an improvement on how your standard Linux system, where there's mutable state absolutely everywhere. There are programs that mutate this mutable state that you don't really know about. Lots of people like to trace their programs to try and find out what's modifying what. There's files in etc. There's files in var. There's files in anywhere in home that get modified, and you don't really understand. You haven't got a simple state model for your machine at all. And then things get, then there's an update process that's randomly updating your code or your operating system. You've got no real model of the state, the code, and this clean separation between the two. So it's kind of, I kind of feel that it's kind of there to make Linux fun again, make it a kind of usable thing, make it something that you can play with, explore. It's reproducible. You can build things fast, even if it's still should be seconds, not minutes, not a minute. But we're getting there. I think that some of the things that kind of I've tried to kind of do while I've been working on this project and tried to think about and tried to be do this compromise between pragmatism and where we want to get to eventually. Try and remove layers from software and systems you're using. Don't try and build everything on top of each other. I think that system software for doing updates and things built on top of things like package management that was designed for humans. And then you built automated tools like Puppet and things that run on top of tools that were built for humans, rather than saying, hey, we're building this for computers, not for humans. We're not trying to use the computer to model the human operator's way of updating a computer. Let's throw away that layer. Let's start again. Let's make something that's an order of magnitude simpler. And that's a kind of my sort of feeling about design for manufacturing. You need to, if things are going to be cheap and easy, you should throw away the layers, don't build on top of them. And I think this is a really important model for all sorts of systems, that there's loads of stuff we do need to throw away, and there's a real tendency to build layers and layers and layers and make things more complicated. And there's times when sometimes you just have to say, no, it's time, that stuff needs to go. Let's do something, minimum viable product style, of throw it all away and see what happens. Most computers that systems that run never have an actual user ever log in, because most of them are just automated and they're doing something. Every now and again, people, I would reckon that we're probably down to well under sub 1% of computer image operating system boots ever have a human log in. Most of them are CI systems and all sorts of things that no one ever logs into, or appliances. The CI system for LinuxKit builds hundreds of machines every time we do a commit, and no one's ever they don't have login shells. You don't log in as optional in LinuxKit. Thinking about things as appliances is. I've spent a long time building appliances to do things, and it's a good way of modeling what you want to do, because appliances are things that just work. They have a function, they do it. Sometimes they go wrong, but you hopefully can diagnose how your appliances go wrong, or you buy a new appliance. And appliances are getting increasingly disposable. And so I find it a great model for building any kind of system is make it an appliance rather than a thing that someone will endlessly tweak and try and keep working. And the whole kind of, having been a sysadmin, I used to log into all these systems and try and keep them working, and it was a nightmare. And just treating things as appliances is just much simpler. Being able to try things out and just really easily when you build a new system, having it so that someone can try it out in 5 minutes. Just get started, try it out, see how it fits with what they want to do is really important to building community. We've had a lot of interest in contributors. We've had I think we're getting up to 90 contributors for LinuxKit in the 6 months since we've launched it, and loads more people who have not contributed because it just seems to do what they want already, which is great. But having that kind of easy steps for trying out a new project are really important. It shouldn't require people to do a sort of great leap and dedication to it when they don't really know it's any use. Making sure that when you launch something that you spend time thinking about how am I going to get people to try it out is really important. Making things kind of simple and helps with that, or just generally removing all the barriers to trying things out. Don't make people fully commit to it, just let them incrementally adopt it as part of their workflow, maybe for some little use case, and then they'll think, oh, this is nice, I like it, I'll use it for something else, and then that kind of grows. It takes time, but it's I think it's really important when you're trying to actually get people to use your code rather than just experimenting, and which is, as I said, something I really like. We haven't lost the war against complexity, but it's a war that we all have to, fight in. I think complexity is everywhere in software, and I really hate it. And there are simple things hiding under all the things that we use, and I think it's really important to not give up in this kind of, there are things that need to be complex because they are complex, but there are loads of things that are complex for bad reasons, because they've been layered on top of each other over the years, and no one has kind of pruned them out and built a simpler version. And if you need to use Linux, and if you're not, use unikernels, please. But if you have to use Linux, try consuming it differently, and that's my kind of real sort of the GitHub repo is there. It's all really easy to use. Try it out. And thanks very much.
Hi there. This looks very interesting indeed. I've got a stack of Intel compute sticks on my desk, which aren't doing much. Is that a piece of hardware that you currently support?
Which one's the compute stick? I forgot.
It's like it's kind of a black rectangular thing about this big. It's like it came out about 3 or 4 years ago, probably now. There's like the newer versions. We've got the first generation one.
Was that? So it wasn't the weird 32-bit one.
Yeah, I think it was. Yeah.
Yeah, we actually don't have any 32-bit support at the moment because. We only went for 64-bit support because we kind of. I think at some point we'll probably get some 32-bit support.
That'd be nice.
At the moment
I'll have to check, but I think it is.
It's not difficult to add, but we basically have support at the moment for x86 64 and ARM64, and we kind of prioritize the kind of server platforms because that's mostly what we use. But now we've got to support for 2 architectures. Adding more is really easy.
Okay, cool. Thanks very much.
Thanks for that. That was very interesting. I'm intrigued by what you said about problem with tooling like Puppet being built as a layer of software above what's meant for humans to use. I suspect the reason it's built that way is so that means that any software that's built for me to use as a human, I can also automate. So I'm curious what you would imagine would be a good alternative to that wouldn't limit me to only software that was built for a manifest for what you're talking about.
Yeah, I mean, I think that there are kind of halfway stages. I mean, I think that, for example, the shell was designed for humans, but we also introduced shell scripts and loads of automation and programming based on shell scripts. And but the functionalities of the POSIX shell for scripting computers versus the human shell for the human to interact with the computers have diverged because the human shell emphasizes things like autocomplete, and this kind of scripting shell often strips those things out nowadays. And there's a useful I can take my idioms from one to the other, but the way they're used has gradually diverged. And some tools are definitely more, some tools in sort of the command line are definitely more aimed at the human. I mean, top is not a scripting command, and so the shell has taken on this sort of richer, interactive model, but it kind of forked at some point from the kind of programming language, and then we got Perl as a better bash in a kind of and kind of in a whole set of we need scripting programming languages, and those two paths kind of diverged over time, and we sort of went to kind of different kind of use cases. And I think there's probably a lot of other things like that. I mean, Puppet are working on loads of ways to use the Puppet tooling for doing things that are not installing packages now. So managing the state of multiple servers, and they're turning it into a more general desired state convergence tool. And desired state convergence is a really important idea in maintaining systems. And so, so I think that there are these different paths that we can take, and we don't have to throw everything away just because we changed our mind about how we want to do things.
Anyone else? Okay. All right, let's thank the speaker.